And now we're going to get to chemical properties, which is reactions. We've talked about substitution reactions of alkanes. Here we've got an alkyl group with a hydrogen, and we have some compound. It could be water, it could be a halogen, and it's going to substitute for the hydrogen. That's a substitution reaction. So it's helpful to look at what kinds of bonds are being broken and made. This bond between the R and the hydrogen, is that a pi bond or a sigma bond?
Sigma.
It's a sigma bond. And this bond between A and B, is that pi or sigma?
Sigma.
Sigma. So we're breaking two sigma bonds, and we're making what kind of bonds? Sigma bonds. So we're breaking sigmas and we're making sigmas. Another kind of reaction is an addition reaction. So here we have an alkene, and we can take that same molecule, but now instead of substituting for hydrogens, we're going to add it. So we're adding this, and we end up with something that looks like that. What bond is missing looking at this? A sigma bond or a pi bond?
Pi bond.
Pi bond. This molecule with the double bond, that double bond is one sigma and one pi. The pi bond now is gone, and in its place are two new sigma bonds. We broke this sigma bond and that pi bond, and then we made two new sigma bonds. So it's really helpful to understand the underlying difference between substituting, okay, I'm going to put this guy in and somebody else comes out, versus adding, where I'm just putting this into it, nothing's coming out, I'm just adding it. Alkenes readily add bromine or chlorine. It's instantaneous, it doesn't need any light or heat. A substitution reaction for the alkanes needed either light or heat in order to get it going. An addition reaction of bromine is actually a useful test for unsaturation. Unsaturation means that there's going to be a double or triple bond. So this little picture here, bromine has kind of a reddish brown color, and if you add bromine to a saturated compound, one that doesn't have any double bonds, you can still see the color of the bromine in the solution. If you add bromine to a unsaturated solution, something that has double or triple bonds, the bromine will add across the double bond, and you'll get a brominated alkane as a product, but the color of the bromine will be gone. So this is a very easy test. You add a little bromine to the solution. If the color disappears, it's unsaturated. Organic chemistry has a lot of little tests like that. So what happens here with the 2-butene is that a chlorine atom adds to one carbon and the other chlorine atom adds to another. So I think of it like this. Here's chlorine and chlorine. And so we're going to end up with one of each of those, and we're going to get rid of this guy. And we're going to get rid of that guy. And then we end up with this. So I think of it as adding across the double bond. One thing adds to one side of the double bond, the other thing adds to something else. So write an equation for the reaction of bromine at room temperature with propene. Well, what does propene look like? How many carbons? 3. Mom eats pickled bananas, 3 carbons. So carbon, 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 there's going to be a double bond in here. And this guy's going to have 2 hydrogens, that guy's going to have 1 hydrogen, and this is going to have 3 hydrogens. And we're adding bromine, Br2. And what happens is that one of these bromines goes on to this carbon, and the other one goes on to the other carbon with the double bond. And that pi bond is gone. So CH2, I'm going to get rid of the double bond. There's just a single bond now. All the original carbons and hydrogens are still there, but we're adding bromine. Does that make sense?
How do you know to add to bromine?
Well, bromine is a diatomic element. It's one of the 7 diatomic elements, and all the halogens, they always go around in pairs of molecules because they're not happy by themselves. So bromine has 7 valence electrons, and he really wants 8. And so he always goes around sharing with a friend as a bromine molecule.
So will most halogens be considered diatomic?
All of them, yes. Yep. And when you have an addition reaction of an alkene, there has to be 2 things that add. Because here carbon has 4 bonds, and here carbon has 4 bonds, and if we only added one thing over here, then we're either going to have a carbon with 5 bonds, or we're going to have one with only 3 bonds, and neither situation is good. And so they're just not going to go for it. Yes?
If you were drawing a line structure and then doing the mechanism, would you draw hooking triangle, double bond 1 to 2, and then draw from bromine to the line to show the break, and then draw off of 1 and 2 the bromines?
We will look at the mechanism.
Okay.
Mechanism's coming. How about 4-methyl cyclohexene? Cyclohexene is a hexagon. Hexene has a double bond. You could draw it anywhere, but then when you number it, 1, 2. If I'm starting with this being number 1, the second carbon in that double bond has to be number 2. I can't call this 1 and go in the opposite direction. 1, 2, 3, 4, 5, 6. Because this is 4-methyl, so then over here on the 4th carbon, I've got a methyl group. And we're adding bromine. Let's see if this will show up okay. So here's our little ghost bromine over there. And 1 adds to this carbon, and 1 adds to this carbon, and the double bond goes away. So we still have cyclohex, but now it's cyclohexane. And it's got the methyl group over here, that didn't change, but now we've got a bromine here and a bromine there. That's just supposed to be a straight line. That's really a sad looking molecule. How would we name that? And it's cyclohexane, right?
1, 2 bromo, cyclohexane, or methyl.
So we've got 2 bromo groups and we've got a methyl group. So it's going to be dibromo and methyl. But we could number from here 1, 2, 3, 4, or we could number from here 1, 2, 3, 4. Who gets the lower numbers, the bromine or the methyl? The bromine. So this is going to be 1, 2 dibromo. We're going to number like this. 1, 2, 3. 1, 2.
That'd be 4.
Yeah, it would, thanks. So apparently I can't count. Pardon me?
Just blame it on the drawing.
Yeah, it's the iPad. I got a new screen protector and it's slippery, and that's the whole problem. Yeah. Okay, 1, 2 dibromo, and I'm not going to have room. dibromo 4-methyl cyclohexane. 1,2-dibromo 4-methyl cyclohexane. Always good to practice that naming stuff. Any questions?
So how would you write out the equation?
I did. This is the equation right here.
Oh, okay.
So organic chemical equations often have structures and not just molecular formulas. Because molecular formulas are not that helpful when there are so many isomers. Another reaction that can happen is addition of water. I think, did I forget a word? Yeah, I guess I didn't use that word. I would have called that previous reaction a bromination, a chlorination. Addition of water is called hydration. So we're adding water. This isn't adding hydrogen, that's hydrogenation. This is adding water. So water can add to alkenes, but it does require an acid catalyst. And so we can think of the water molecule as being H on one side and OH on the other. And so the H is going to add to one side of the double bond and the OH is going to add to the other side. And what you end up with is an alcohol. This is ethanol. Alcohol has the functional group OH. So this is ethene with water added, and we have a little H plus up here because it will not happen unless there's a catalyst. And then we end up with ethanol. Here we have cyclohexene. They wrote the H's out just to show you what's happening when we're adding the water, and the hydrogen adds to one side of the double bond, the OH adds to the other, and we end up with an alcohol with that OH group on there. Write an equation for the acid-catalyzed addition of water to 3-hexene. So 3-hexene, that's hexane with a double bond between the third and the fourth carbon. So CH3, CH2, this would be 1 CH, there's the third carbon, double bond, 4, 5, 6. Yeah. So the double bond's right in the middle. So there's 3-hexene plus water, an arrow with an H plus over it. And then this probably isn't going to fit over on the right, so I'll just kind of draw it below. What happens here is that hydrogen adds to one side and the OH adds to the other side. So this is it's like a ghost here. This is going to come on one of the carbons and the OH is going to go on the other one. So then for my product, I've got CH3, CH2, CH. I'm going to draw that as an H just so we can see what happened. This is.
So it would be just a CH2 also?
Yeah, you could definitely write it as just CH2. Actually, maybe what I should do is just make that a different color. This is the part that got added. You could definitely include this guy up here and just say CH2. Definitely. Any questions?
Wouldn't it need another bond?
It does have another bond. You're talking about this carbon?
Yeah.
This carbon is bonded to this hydrogen, that's 1. This hydrogen is 2. That carbon is 3. And this carbon is 4. It's a little hard to see. So this is that part right in the middle. And what's happening is that we've got the H coming in here and the OH coming in there and the double bond going away. So how about 2-butene? Butene, 4 carbons, right? Double bond on the second carbon. 1, 2, 3, 4 carbons. This one's, I'll draw this one a little more stretched out. So this has, here's our chain. This is carbon 1 and 2. There's our double bond. This carbon has a hydrogen, and that carbon has a hydrogen. And we're adding water to this. With an acid catalyst. So this one is adding here, and this guy is adding there. I picture it a little, I mean, these model kits are really great. Because we're breaking this off, and we're sticking hydrogen on one side, and the OH on the other side. Doesn't want to stick on there. So I had a double bond here, I open up that double bond and I put a hydrogen on one side and I put the OH on the other side. How about 4-methyl cyclopentene? Now I've really run myself out of room. Well, cyclopentene is a pentagon. It's got a double bond. The double bond has to be 1 and 2. So I'm going to call this bottom one 1, 2, 3, 4. So I've got a methyl group over there. And adding water to that. I've still got the methyl group. I've still got the basic shape of the ring. But where the double bond was, I'm going to put a hydrogen on one side and a hydroxide on the other. An OH. It's not really hydroxide. Now, normally we wouldn't necessarily draw the one hydrogen because we didn't draw all the other hydrogens. But I left him on there so you can see what happened. Hydrogen went to one side of the double bond, OH to the other. Any questions? Yes?
How do we always, or how do you know which side to put the OH and which side?
That's an excellent question. We'll get to that. That's a very good question. We can also have acids add to alkenes. Same pattern. But now instead of HOH, it's HA, where A is just the anion of the acid. The hydrogen adds to one side, the ion of the acid adds to the other side. This works with hydrogen halides, so HCl, HBr. It also works with sulfuric acid. Sulfuric acid is H2SO4. And for the purposes of organic chemistry, we think of it like that, where this is the hydrogen that's going to add to one side, and this big old thing is going to add to the other side. So write an equation for each of the following reactions. 2-butene plus HCl. So butene is pickled bananas. Mom eats pickled bananas, 4 carbons. So carbon, double bond in the middle, plus HCl. And then we're going to end up with our original thing here. I'm going to change colors here. Make the HCl a different color. And so we get H on one side and Cl on the other. Three hexene. Let's try a line angle. See how that goes over. Hexene is 6, right? So 1, 2, 3, 4, 5, 6 carbons. On the third carbon, this is 1, 2, 3, there's a double bond. So that's 3 hexene plus HI. I want to do a different color. So the hydrogen is going to add to one of these carbons of the double bond, and the iodine is going to add to the other one. And if we're going to keep with our line angle drawing, we're not going to 1, 2, 3, 4, 5, 6. So these are the carbons involved. One of them gets a hydrogen, and we're not drawing any hydrogen, so I'm going to leave him off. And then the other one gets an iodine.
Why did you leave the hydrogen off?
Well, he would be here, and he is there. But then if we're drawing the line angle, we usually don't show any hydrogens, because there are hydrogens all over the place. This one has 3 hydrogens, this one has 2 hydrogens, this one has another hydrogen besides that one. So this is a little more sophisticated. Like, we're not going for sophisticated, we're going for simple. Okay, I'll make him darker.